Hello everybody, hello students, hello whoever watching the video. Welcome once again to Dr. Saurabh Sir's classes. We were continuing the videos on group theory, students, and you already know how much we have covered. I don't have to tell you that. Okay, we have covered quite a lot on group theory. We have done quite a lot of examples, quite a lot of study part, quite a lot of mathematical part. Okay, and we have reached so much that we have reached a part of cyclic groups, non-cyclic groups. In the previous video I spoke to you about non-cyclic groups, if you remember. I can go back to the same page and show you. Okay, this is exactly what we had done. Yeah, what we had done in the previous video. Lot of scribbling over here, but you may not be able to understand from here what happened. Okay, but if you go back to the video and you follow the video, you will definitely understand what went around here. Okay, so today we are going to start with our next part, and that will be some important results on cyclic group. Students, I want to tell you that in these important points, there will be many important points. Okay, the 5 of them that you see over here is just a start. Okay, so there will be many important points or important results on cyclic groups, and I will try my best to give you mathematical examples on parts which require mathematical examples. But in case I will do it. I will not say something like in case if I cannot, okay, or in case if I cannot give you if I don't want to give you a mathematical example or something like that. We'll not do that. We'll try and give you a mathematical example as much as possible. Okay, so moving on to our first point for today is this. Let's select a beautiful color, and the beautiful color is red. Okay, the number of generators of a cyclic group G. Understand, again I am saying the number of generators of a cyclic group G of order n is equal to phi n. What is that? That is phi n. It's a function. Okay, where phi is a Euler's phi function. What is Euler's phi function, students? If you know what is Euler's phi function, it is this. Okay, look very carefully. Euler's phi function of n is given in this way. It's given as let me remember. It's given as 1 minus 1 by p, something like that, where p are the prime factors of n. Okay, now what is this n? Suppose I'll give you an example. Okay, give you a mathematical example. Let's say n equal to 6. So what is the Euler's function telling you? That is 6. Now do the HCF of 6. That is 2 3s are 6, 3 1s are. What are the prime numbers you are getting? 2 and 3. So what can you write this as? You can write this as 6 into, okay, 1 minus 1 by 2. Okay, now and then it will be again into 1 minus 1 by 3. That's how it is. Okay, that is how the Euler function works. Alright, more or less that's how the Euler function works. That is the basic example, a small little example for the Euler's function. Okay, a very big mathematician, Euler. I don't think anybody can match his level, and that's why he has given many type of functions. Euler's zeta function is also there. Okay, so we are talking about the phi function. Let's stick to that. Let's move on to the second one. What does the second one say? Converse of Lagrange's theorem. Converse, not the shoe. Okay, not the shoe that you wear on. Don't think about Converse shoe. It's not a shoe. So you know, converse of Lagrange's theorem is true for finite cyclic groups if D by the order of G, and G is a finite cyclic group generated by X, then G has a unique subgroup of order D generated by X to the power order of G divided by D. Okay, that's how it's written. X to the power, let's rub these lines, then you'll be able to see better. X to the power, this, let's use a highlighter. Hold on. is it? Highlight a color. Let's select a lovely color, let's say yellow. Okay, so what does it say? Converse of Lagrange's theorem is true for a finite cyclic group if D by the order of G and G is a finite cyclic group generated by X. G will be a finite cyclic group, it will be generated by some element X in G. Then G is a unique subgroup of order D generated by this. Make sure you keep this in your mind. Okay, the group will be generated by that type of a formula. We're moving on to the next one. Every cyclic group is abelian, but the converse is not true. What does that mean? It means that every cyclic group, every group that is cyclic is abelian, not Abetian. I don't know why I have a habit of putting the, see, the whole word went away, the T's head was only left. What type of things happen? I mean, abelian. Okay, so what does it mean? Every group that is a cyclic group is abelian, but every group that is abelian is not cyclic. Okay, does not mean it's cyclic. Let's go and try and understand example. The Clen 4 group EABC is abelian but not cyclic. Why? You will not find a generator. You will not find that every element can be generated by one of them. One element over there is generating all the elements. You will not find a possibility as such. You can go ahead and check it out. Every time you check it out, you will not find anything as such. So that's why they are saying that, okay, they found out, while the mathematicians were doing all these things, they found out that the Clen 4 group, the K4 group, this is called the K4 group, Clen 4, K4 group, that contains elements like EABC, is abelian but not cyclic. Okay, it's abelian but not cyclic. That means every cyclic group is abelian, but every abelian group is not cyclic. Make sure you keep that in your head. Very, very important point. Okay, I would like to mark this as very, very important. Okay, let's rub out some of these parts over here. I want to mark this point for you as very, very important. Let's rub off. I hope you've understood the phi function. You will just copy it down in your book. Okay, so mark this as important, because they will ask you a question. Suddenly I might want to ask you a question. Is it necessary that every cyclic group is abelian? They will ask you a question. Then you will say, yes, every cyclic group is abelian. Then they will ask you another question. Suppose they ask you another question. Give an example of a group that is abelian but not cyclic. What do you write? It's the K4, Clen 4, with the elements of EABs. Small answers. Okay, the theory part will have small questions, just asking you selective questions. Okay, tell this. Okay, tell that. So don't need to worry. Okay, don't have to worry about anything. Let's move on to our fourth one. Mark this as important. Let's move on to our fourth one with the highlighter again. An infinitely cyclic group has precisely two generators. An infinitely cyclic group means a cyclic group that is extending to infinity. Extending to infinity has how many generators? Two generators. So they will ask you a question as such. If I have an infinite cyclic group, how many generators can I find? Precisely two generators. Okay, you will write that word precisely also. Don't forget about the word precisely. You will write precisely two generators. Okay, to be exact, that's what they are trying to say. To be exact, there are two generators. Okay, moving on to our next one. Every group of prime order means prime numbers, okay, is cyclic, and each element except the identity acts as the generator of the group. So what does it mean? Every group that is of prime order, prime numbers, what are they? 2, 3, then 5, 7, then 8 no, 9 no, 10 no, 11, right? So all these they can generate, right? They can generate these values. Like say if I do 2 plus 3 plus 5, 5, 6, 7, 8, 9, it's coming 5, 6. If I multiply this 15 to 30, these what does it say? It says every group of prime order is a cyclic group and each element except identity acts as the generator of the group. So you can generate the group with let's say 2 plus 3. Okay, let's not add 3 of them together. Let's say this part is 2 plus 3, right? 2 plus 3. So what do you get? You get 5. You get the prime number, right? Now if you do 5 plus 2, then you get 7, right? Now if you do say 7, 8, 8, 9, 10, 11, then if you do, let's say yeah, here we have done 5 plus 7, then we can also done 5 plus 2, that is giving us 7 over here. So you can see that they are generating, right? They are generating values of the group. Okay, they are generating over here of the group, but the identity element, okay, but the identity element acts as a generator except the identity element. Every element acts as a generator, okay, except the identity element. When we do the questions, right, when we go ahead and do the questions, I will show you an example. Okay students, now so it says every group of prime order, okay, this example would be wrong, rub this off. It says every group of prime order. I read that wrong, okay, please don't mind. I'll just tell you what this is trying to say. A little mathematical example is good, okay, little bit mathematical example is good. Every group of prime order is cyclic, okay. So order of the group is prime, okay, order of the group is prime, P. That means order of the group is, say, prime number, say 5. That means there are 5 elements in the group, and whatever these 5 elements are, they will generate the group. Except the identity element. So you can find a group which will have an order of prime number, okay. So whatever these elements will be in the group, they will, okay. What is the least prime number? 2, of course, isn't it? That's the least prime number, right? That is the least prime number. So if that is the least prime number, then that means this 2 belongs to the group G, right? So if suppose there are 2 elements in the group G, okay, then order of the group G will be what? Order of the group G will be 2, of course. Yes or no? That means it's prime, okay. Hence those 2 elements will generate the group. Those 2 elements will generate the group. No matter how many elements are there, no matter what the elements are, doesn't matter, okay, they will generate the group. And the A will not be equal to E. Any A that belongs to G will not be equal to the identity, okay, will not be, the identity will not generate anything here. It will not be counted as the generator in this group. So I hope you have understood the mathematical part of this, okay. Little bit example was little different, but it's okay. We can understand this example, okay. I will give you more examples on these type, how the order of the group is prime, and then you can find that the group is generated by each element. The basic concept is you understood how the elements are generating the group, right? So since you have understood how the elements are generating the group, it's very easy for you to, when you get the question and they tell you to find the generator, you will easily find the generator. Then you know that which element over there can be used to find all the elements, right? Which element can be used, like if there are two elements, okay, let's say 1 comma, say 1 comma 2, okay, just taking any vague example, okay. So if I do 2 plus 1, then I get 3. Yes. If I do 1 plus 1 plus 1, then I get again 3. Okay, so you see the elements are generating somewhat the group. Okay, so the order of this group is what? The order of this group, this one here, is 2. Order of G is 2, right? So that's how it's happening. I'll give you more example, you don't need to worry. Okay, just go through these notes. Okay, then example time, we'll give lot of examples, don't worry about that. Okay, a lot of mathematical examples are waiting to come, because we haven't started the mathematics part yet. We are just continuing with the theory. Once we start understanding the theory and we have learned it properly, we will start with the mathematics. Okay, you don't need to worry about the mathematics part. Okay, so anyway students, that's it for today. We will continue this in the next video. Okay, you keep taking as much help as possible from our classes, because all the help that you'll be needing will be provided here at Dr. Saurabh's classes always. Thank you for watching, students. See you in the next video. Bye bye.